Hi everyone. Today's lecture will be on sampling, quantization, and image enhancement. We'll cover two parts. The first one will be on sampling and quantization, and we will study discretization, continuous signals, signal representation in the frequency domain, and effects of sampling and quantization. In the second part, we'll talk about image enhancement, which will include noise suppression, deblurring, and contrast enhancement. I'll try to upload small videos in the Moodle platform, so it will be easier for you to download and study. Let's start our discussion with the sampling and quantization part. Remember this picture? I think you've seen this in the previous lecture on how to convert photons into digital signals. What we see here is actually a CCD camera and a CMOS camera structure. In both of these, we've seen that there are these sensor arrays where at each part, all the photons that fall in this rectangle are covered, they're all retained, they're converted to electron, and then to voltage, and then the voltage was converted to digital signal. Now there are two things happening here. First, in all of this area, we're actually gathering photons from multiple areas in this region, but we're representing it with only one value. So in essence, we're using a spatial discretization. Second, when we convert this value into a digital signal, we basically convert a real valued intensity or brightness value into a finite value represented by a certain number of bits. So both of these are required for discretization or digitization. They're necessary for us to be able to represent images in a computer and process them. And they really include two parts. As I said, the sampling or the spatial discretization's role is to create pixels. We're actually talking about a grid structure, and we're representing all the photons that fall in each of these cells with only one value. And we do it for multiple areas to cover the field of view that we have. The second part is the quantization or the intensity discretization, and its role is to create gray levels. The number of photons that fall in this area can be varying quite a bit. In the extreme case, it's actually a real valued signal that goes from -infinity to infinity, but we cannot represent such real value signals on a computer. So what we do, instead, we basically use a finite number of levels and represent the gray value with finite number of gray levels. Essentially, for each of these grid points, we assign one of the gray levels that we actually have in a sense in our dictionary or our quantization levels. The sampling and quantization are already there whenever we look at a digital picture on our mobile phone or on a computer. For example, an image we have here, we can actually see the effects of sampling and quantization simply by looking at a certain area and enlarging it artificially. What we see here is that we have certain blocky artifacts. Here, this edge looked very straight, but when we zoom in the picture, we see actually it's not straight at all. It's actually created by these rectangular grid points, and that's the effect of the sampling. Moreover, we look at that there are actually some discrete, very abrupt changes in the gray levels, where actually we know that this is the air, so the brightness should be quite homogeneous or changing very slowly. Instead, we have these blocky artifacts, which actually is the effect of the quantization. If I were to look at this picture in terms of the numerical values, I would actually see that I only have a certain number of numerical values, each of them corresponding to intensity in the pixel. And notice that the values themselves actually are not in continuous value, but they go from 0 to 255 in this case. Now, it's necessary to create a finite number of points in space, in a grid, and intensity values in each pixel, and represent them with finite number of bits in the computer. Notice that the original scene was actually in continuous space and intensity values, but we cannot represent it in the computer. So digitization really applies both of the sampling and quantization automatically. Let's see the effect of sampling and quantization a bit further. On the top left, I show the same image at its highest resolution. So we see that actually it's quite nice. We see the edges, we see all the details. If I reduce the number of pixels I use, here I use 384 pixels by 288 pixels, Instead, if I use 192 to 144 pixels, I see that I start losing some information. I see more of these blocky artifacts. It's still fine, I can actually recover what's happening in the image more or less, but the quality is less. Going one step further, if I use 92 by 72 pixels, for instance, now I see the large pixels, they become very apparent, and I start really losing the information in the image. I can still recover what's there, but it's harder. Taking it to the further extreme, even interpreting what was in the image becomes impossible. Now I clearly see very large pixels, and the fact that very few number of pixels are used to represent the entire image. We can also look at the effect of quantization in a similar way. This time, in the bottom left corner, we have the original image, and it's actually represented using 1 byte per pixel, so 8 bits or 256 gray levels per pixel. And I see it's very nice. Even the homogeneous areas are nicely represented. I can see the clouds, I can see details. If I reduce 256 levels into 8 levels, I actually see that nothing really changes much. I can see the details. You really have to look very carefully to see the effects. One area it's quite easy to see the effects is the clouds. Notice that now in these homogeneous areas, instead of having a very smooth transition, now I actually see discrete changes. Now, to take it even one step further, I can actually use only 4 levels, so 2 bits to represent each pixel's intensity values. Now I see that before, areas that actually showed intensity variations are now represented only a single value. Funny enough, the details on the edges and corners are still there, so I can still make out what's happening and what was seen in this image. But all the fine-level textures, fine-level details about intensity variations are completely gone. I can take it to another extreme and only use 1 bit to represent intensity values per pixel. Then I would get a binary image. There's not much information about the gray levels, they're all gone, but the edges and corners are still visible, and you can still make out, for example, what was seen in this image to some extent. Now we can actually examine these effects with a much more controlled example. Here we have a background that's completely white, and we have the foreground that actually is selected to have very fine level details. Again, if you look at the effects of sampling, meaning that at the top left corner, we actually have the image at its full resolution, and we start decreasing the number of pixels used to visualize and represent the image. And we see that at each point, we start losing some level of information. We start, for example, just by reducing the pixel size by twice in both directions. We see that we're not able to now represent perfect circles. They instead became blocky artifacts. If I reduce the number of pixels even further, now I lost complete the fact that there were circles. Now it looks like there were squares or rectangles at the beginning. I can also see that actually the wheels are gone. The details are very hard to recover. Even reducing the number of pixels, I start losing all the information. I can look at the effect of quantization again. On the top left corner, I have the same image, and I start reducing the number of bits used to represent each pixel's intensity value progressively. What is interesting is that the effect of reducing the quantization level does not have the same effect as the sampling. The details about the geometry of the objects remains the same. I can see that a circle is a circle here and a circle here, and that's quite nice. It's only actually when I go to the extreme that small intensity variations around that circle start causing a problem. The major effect, however, is actually seen in the areas where I had homogeneous transitions or shadows. For example, here, or here. If I start reducing the number of quantization levels I used to represent the pixels, I see that areas that were homogeneous before now have sharp artifacts and sharp changes. I want to make three remarks on this topic. One of them is the use of binary images. So the binary images seems like a very extreme case. However, they're actually quite useful in industrial applications where usually people have full control over the imaging conditions, meaning the background color, the lighting conditions. If I have an object that I manufacture, I can actually make sure that the background is completely black, for instance, and the foreground is well illuminated, so the boundaries of the objects are clearly visible. If I want to assess whether there are any problems in the boundaries, I can actually use a binary image because all I'm interested in is really fine level details in the boundaries. And as we've seen, using quantization, even binary at 1-bit quantization levels, I can actually see those changes and see the details on the edges and the corners. The second remark is about the uniformity of the sampling and the quantization schemes. In these examples, we've seen that we use the same size of pixels and the same number of bits to represent intensity in each pixel across the image. But this is a choice. You can actually use non-uniform sampling and quantization, and these are used sometimes for specialized applications. What I mean is, for example, if you have an image where you have lots of homogeneous regions and few edges and corners, you can actually use fine sampling to capture those details in the edges. So use smaller sized pixels where edges and corners are, and use larger sized pixels in the homogeneous areas. Likewise, if you want to capture homogeneous transitions and gradients in the intensity levels, then you can actually use fine quantization levels at that area, and low quantization levels or coarser quantization in the edges and corners where you're guaranteed to capture the changes in any case. Combining these things, actually you can really control how well you represent an image and capture the details. The last remark is on the sampling strategies. So far we've only seen the grid sampling, but different sampling strategies exist. In theory, you only need regular and image covering tessellation. And you can actually obtain such an image covering tessellation using 11 different polygons. But if you want to use the same polygon across the image, then you really have only 3 options if you want to have a full coverage. And these options are shown on the right. You have the rectangular grid, the triangular grid, and the hexagonal grid. The rectangular grid is obviously the most popular one and used everywhere, partly because the production of those sensors are easier. However, the hexagonal grid has certain advantages over that, and one of them is that it's more isotropic, and I actually have no connectivity ambiguities. What does that mean? When I talk about the connectivity between neighboring pixels in the rectangular grid, well, I have two different types of connectivities. One is pixels that actually share the same edge, like those ones here for the central pixel, and ones that share the same corner. Now, obviously, these pixels are not connected in the same way. So whenever you talk about the neighborhood of a pixel in a rectangular grid, things can become a bit ambiguous. You have 2 different neighborhoods. In a hexagonal grid, however, you only have one type of neighborhood. Or if you have a grid pixel here, you only have pixels that share an edge with that pixel around it. And there are no other connectivity patterns. So that's quite nice. Actually, somehow, this similar hexagonal grid structure is seen in the retina of various species in nature. So somehow nature prefers a hexagonal grid structure over a rectangular one. At this point, before we delve into the sampling and the quantization independently, let me actually stop this video, upload this part, and I will start the other part with another video.